Okay, path of reaction, effect of a catalyst. So the equilibrium constant tells us how far a chemical reaction will go, the balance between reactants and products. The reaction rate is what's going to tell us how fast it's going to get there. You could have the equilibrium, but it might take a year to get there, or it might take half a second to get there. That depends on the rate of the reaction. We talked about how when those particles collide, they have to have enough energy. And we talked there's a barrier that has to be overcome. We call that the activation energy. That's the energy barrier that needs to be overcome in order for the reactants to be converted into products. So with the people in the video running into each other, they have to run into each other with enough energy to knock the arm off of the one person onto the face of the other person. Activation energies do exist for most chemical reactions because we usually have to break some bonds before we can form new bonds. And so there's got to be some energy involved, and the energy comes in form of collision energy. So this is an energy diagram where we're representing higher energy being higher on the y-axis and the reaction pathway going across to the right here. Here's the energy of the reactants. And so for this reaction to occur, what usually happens is that the energy of the reactants is higher, the energy of the products is lower, and it's like rolling down a hill. Things go downhill because that's going to lower potential energy. But before it can roll down the hill, it has to get over this hump, and the hump is the activation energy. This reminds me of playing miniature golf. So here you've got a person playing miniature golf, right? There's your golf club. And this is one of those little humps on the green, right? And you have to hit the ball with enough energy to get it to go over the hump. If you hit it with too little energy and it's moving too slowly, it'll go partway up the hump and it'll roll back to you. And you just lost a stroke, right? So we have to have enough energy to get over the barrier. Once it gets over the barrier, everything's good. It's all literally downhill from there, okay? At a given temperature, the higher this activation energy, the slower the rate of the reaction is going to be. So if you imagine maybe a really, really difficult golf course, or maybe a young child playing on the golf course, and they're having a hard time hitting the ball hard enough to get it over the hump. The higher that hump, the longer it's going to take to get the balls over. If the hump is very low, then it's going to be really easy to go over, and the reaction will go very quickly. Higher activation energy, fewer reactant molecules are going to make it over the barrier, and so the reaction rate is slower. Does that make sense? Well, what can we do to speed up a slow reaction? Is there anything we can do? Well, you can increase the concentrations. That increases the number of collisions in a given amount of time. It doesn't do anything to the energy of those collisions, but some of those collisions will have enough energy. It's like a percentage, right? Maybe 5% have enough energy at this temperature. Well, if we increase the number of collisions, then we're going to increase the number that actually have enough that get over. So that's one way. Another way is to increase the temperature. Increasing the temperature results in more collisions and also higher energy collisions, so that will increase the rate of the reaction. Or we can do something about the barrier itself. What if we just cut the top of that hump off, made it lower? That would make the reaction go faster. That's what a catalyst does. It doesn't cut the top of the hill off, but it provides an alternate pathway that's easier. And some of those miniature golf courses have things like that. You can try going over this big hump, or if you hit it over here, it'll go around in this trough and go down really easy. The analogy the book gives is pushing rocks off a cliff. So without the catalyst, we've got to push the rock up and over this hill before we can get it off the cliff. This is the activation energy here. With the catalyst, that hill's still there, but now there's a path that we can go around the hill. We can go around, and so it's gonna be much faster to get those off the hill. Those are looking like meatballs to me because I didn't get any lunch yet. So increasing the reaction rate by pushing harder would be like increasing the temperature. I'm just going to put more energy into this. I'm just going to really get pumped up, and I'm going to push these harder. I'm going to get them off faster. Finding a path that goes around the hill is using a catalyst, finding an alternate lower energy pathway. So working harder and working smarter. So the effect of a catalyst is to lower the activation energy. That will cause the reaction to go faster. Enzymes are biological catalysts. Your body is a chemical factory, and there's just thousands and thousands of chemical reactions occurring to sustain your existence. Many of those reactants are thermally sensitive, meaning that you can't just speed up the reactions by increasing the temperature, right? Because if you increase the temperature too high, the proteins will denature, and that kind of defeats the purpose of trying to stay alive in the first place. So how do you get the reactions to go at a faster rate? You use an enzyme, a catalyst. Most of those reactions that are occurring would occur too slowly, just at normal body temperature, and so the catalyst is really important. The catalyst also then serves as a control on the reaction. Your body can control whether this reaction occurs or not by turning enzymes on and off. So sucrase is an enzyme that creates a lower activation energy pathway for the conversion of sucrose into glucose and fructose. So sucrose is a disaccharide. It's got two different sugars that are joined by a bond. And to metabolize the sucrose, you first need to break that bond and get it separated into glucose and fructose. It requires energy to break the bond. This is the activation energy. At room temperature or even at body temperature, that reaction is going to be extremely slow, and you're going to die before you can metabolize the sugar. But your body uses sucrase, an enzyme. The enzyme has this little, like a pocket or a nest for the sucrose. It's the active site. So the sucrose fits in here, but as it fits in here, in order to fit, it has to get strained a little bit. That bond is like stretched or bent. It's just a little bit of strain. That makes the bond easier to break. So when the sucrose is sitting in the active site, it's easier to break the bond. That's lowered the activation energy, so we break the bond. Once the bond is broken, the glucose and the fructose go off, and the enzyme is there to catalyze the reaction of another one. So one thing important about catalysts are not reactants or products in the reaction. They are, they make the reaction go faster, but they are not used up in the reaction. So they can facilitate things over and over and over again. Well, I guess that one does have more space. Another analogy for this is if you think about, here you've got a fence. Okay, you have a fence in the field, and for whatever reason, we need to get this bunch of kindergartners on the other side of the fence. And it's the type of fence that you can't just like crawl through the slats. We have to get over somehow. So you think about all the kindergartners running out here, and they're trying to get over the fence. They're little, right? Some of them are afraid of heights. This is a tall fence. It's going to take them a while, right? How can we speed up getting them over the fence? Sugar. We could give them more energy, yeah. Or we could put a teacher here to help them over the fence, right? So you put a teacher here to help the kids over the fence, and they're going to get over faster. The teacher is just there and helps child after child after child after child. Maybe gets tired, but the teacher doesn't disappear. The teacher isn't a reactant where it's one teacher for every child to get over the fence. The teacher's just the catalyst. It makes it easier for the kids to get over the fence, and so they can get over faster. So catalysts speed up reactions, but they're not consumed by reactions.